Because one of the disadvantages of virtual circuit is that you must do this call setup first on this new technology now. So instead, they have what's known as the permanent virtual circuit, and slightly different to the virtual circuit. Remember, every time you want to transmit data using virtual circuit, you must do this call setup, send this packet first. But now they come up with this idea with permanent virtual circuit. They say you only do the call setup once, and hopefully you may not have to do it again for hours or days or weeks. So for example, if you send a request to this router, say I want to call a user here, from this user A to that user B. Normally in virtual circuit, in the memory of this router, it will maintain or keep a record of this call. And it will pass the request to another router, which hopefully, if it has and approves the call, it will also store the information in its memory, main memory. And similarly with every router until it got there. So now all the routers know about this call, just like booking a flight. All the computers or all the airlines or whatever, they know about this trip. Now, what happens if this router dies down, powered down for some reason? It lost power. It will shut down and it will reboot. When it reboots, what happens to the information in main memory?
Lost.
It gets lost. It's a volatile memory. So when it wakes up, when it's booted up again, it does not know about any of the calls that have been through it. And what happens to all these virtual calls? They're all terminated. So they came up with this idea, the permanent virtual circuit. They say if the user requests a permanent virtual circuit, it follows the same thing. You go, find a space, put it in your main memory, but also save it onto the hard disk because it's permanent. And then if it's forwarded here, also, we require that this piece of information is saved in a table or in a database on the hard disk. And we continue working with the main memory. But if this router goes down for some reason, and it boots up again, first thing it does is say, do I have any virtual circuit, any permanent virtual circuits? And it looks up at the database, and when it boots up, it fills up those 2 or 3 or 10 permanent virtual circuits, so it knows about them. So if it shuts down and comes back up again, it still knows about your call, and you don't have to make another call. And this is known as the permanent virtual circuit. So it's very similar to the virtual circuit, except the information about that particular call is saved onto the hard disk. So if that router shuts down at night, or if for some reason it accidentally was turned off, when it boots up again, it has to go to its database and see if there are any calls going through it, loads them into its main memory, and they're still available. And this way, when you make a call setup, you can have it for days or weeks or months or even years. You don't have to do another call setup. And this is one of the disadvantages of virtual circuit, is that you have to do a call setup. Now they tell you, you don't have to do it. Okay, you do it once, but it might be valid for years. You won't have to do another call setup to the same destination. Okay, so this is known as the permanent virtual circuits.
And is there any semi-permanent virtual circuit or just permanent?
No, just the virtual circuits and the permanent virtual circuits. And the difference between them is that the permanent virtual circuit, the details about the circuit or the call, as well as being kept in main memory, it's also saved onto a hard disk. And it can be used again if there is a power failure or normal shutdown and normal operation.
So you said there that maybe days, weeks, or months that the call setup will have to be done. Is there a scenario where it might have to be done again? The hard disk?
Yeah, if somebody, well, if the hard disk goes down, yeah. But I imagine most of these places will have a backup for a hard disk. But yeah, if the individual, the receiver or the sender decides, I'm going to clear this call. If they send ending the call, all routers will wipe it off their memory, and they'll also wipe it off their hard disk. And to get to the same number again, you must do another call setup. Okay? And normally, even with virtual circuits, you can start it in the morning and leave it. You don't have to switch it off. It's only if one of the routers go down or reboot it, you won't have a record of it. It'll be terminated. But at least with the permanent ones, there'll be no... Any questions? Everybody kind of understands them a bit? Yeah. Good. Once you have the logic, yeah?
What kind of networks would you use the switching, the virtual switching?
The virtual switching. One example is known as the ATM ATM network. And it provides high-speed networks. And it's actually used by the internet. Sometimes they say, listen, we have a lot of data between here and Australia. Can you carry this data for us? So it carries it and it hands it over to the internet company on the other end, and then the internet delivers it to the end user. So they are available and they're still in use. The internet is just one of many networks around the world. It's the biggest, obviously. It's the most used network. Any other questions?
The datagram switching technique, when the data are fragmented, do they take into effect the size? Or just bring anything?
The size, the reason why this jump in speed in delivering data is that we no longer use hard disks or tapes to store a message at each computer. Everything happens in main memory of computer. So as long as the message fits into the main memory, it will just fly through. Main memory uses speed of electrons, which are possibly about 2/3 the speed of light. So they're extremely fast. Things can go around the globe in less than a thousandth of a second. So the size of the message is important. But what also is important, remember when you make a booking and you fly and you go to London and you don't know where's your gate or you don't even know where you're going.
Yeah.
Yeah. They don't ask you what is your name. Your name means possibly nothing. They ask you for that booking code. So once you give the booking code to British Airways or Air France, they can key it in. They say, oh, your name is Tom, by the way, just in case. And your final destination is going to be wherever it is, Istanbul, but your immediate now hub is going to be to Rome, and it's on gate number 16. That's what happens here. When only in the first message you put your full address, source and destination addresses, and that's in order to book all the routes right through. But after that, you take the message, break it into smaller packets again, and you don't have to put the source or destination address anymore. All you have to put is that booking code, which here we call the virtual circuit or the virtual circuit number. So you just write 77 on these. So as you can see here, the header is reduced a lot in this system. And therefore, this is more efficient at carrying data. If the channel can deliver 1 million bits per second, most of those 1 million bits are going to be user data, not redundant data. Redundant data is data that's not sent by the sender. It's been generated by the system and it's cost the system. It's like if you run a bus service from Dublin to Belfast and there are 50 passengers or 50 seats on the bus and they all pay 20 euros each or 50. So you get a lot of money from 50 passengers. But if, for example, redundant, now I'm talking about redundancy, you say the bus might break down, we need to carry 4 mechanics onto the bus. So 4 seats are gone, they're being used by mechanics who are extra weight you're carrying. They cost you petrol and fuel and all that, and you lost the income from those 4 seats. That's called redundancy. Here, the redundant information is a lot less than the datagram switching technique. So it's a lot more efficient at using the channels that are available. Most of the data, it has a smaller header, basically. And if it has smaller header, remember, main memory, if this router has this much main memory, how many packets could it fit in there? Let's say it can fit 4 packets because they have huge headers. If they didn't have that much header, they'd probably be able to fit 8 headers at a time, and they're flying through. So smaller headers, better operation, because it requires less memory from those routers sitting there. Any other questions?
What's the key difference between datagram switching technique and the virtual?
Those two techniques that are in use today, the key difference between them, anybody can point out? Yeah?
The size of the data, one is bigger than the other because it doesn't carry redundancy.
Yeah, this one, headers are smaller than this headers. Yeah, but that's not a major difference. It will cause a bit of performance. Hold on, yeah. This one provides a quality of service. This one guarantees a quality of service. This one cannot and does not guarantee a quality of service. Something else. This one is built on the basis that if you want to make a call, request it first, we'll confirm it to you, start sending data, and every data is delivered from here to there. We'll acknowledge it. When it's delivered to the next one, it's acknowledged. If it got to the end, we'll give you an acknowledgement. If it didn't get there, it will give you an acknowledgement. So it's designed around the idea of acknowledgements and confirmation and things like that. So is that a good thing or a bad thing? Let me ask a question. Is it good for a network to give acknowledgements and we can't send something until you request it first? Or is it bad?
It's good to make acknowledgement.
It's good. Anybody thinks otherwise? It will put more load onto the network, but you are a user. Are you interested in, from a user point of view? Let me think of it from a user point of view.
If you don't want to be traced, maybe?
Say again?
If you don't want to be traced, something.
If you don't want to be traced, okay. Let's say that's out of the question. We want to trace. Okay, any other? Yeah, that's true. It's easier to send data and you may not be traced on the datagram switching technique. You can switch. Of course, we know that every packet you send will carry the source address, so we know who sent it. But, of course, you can have applications that will modify that source address, and then they will not know who it came from.
If you don't get a receipt, well, then you don't know to transmit information that's missing.
No, you won't know whether your message has been received or not received. Yeah, but that's the question. Is it a good...
It is, so you can resend it. If you are doing a transfer to your bank or somebody's paying you and a piece of information saying how much money you're actually paying is missing.
Of course, yeah. So it's normally acceptable that you need a confirmation, especially if you're doing an official business. Anybody has any different ideas? Where the other way is better, where not acknowledgement, no confirmation is a better way than acknowledgement and confirmation.
One is faster than the other.
Well, speed, yeah, it depends. See, this one, yes, it can affect speed. This one depends on the number of users. But yeah, it will have that effect on speed. I'm not talking about speed now. Okay, any other reason?
Redundant data, less memory required. Less redundant data, less memory required if you don't send acknowledgement.
No, we'll see if you're sending the same, okay. There's one other, did you have an idea or another example?
If you're publicly sharing data, then anyone can access it instead of sending
You have to request it beforehand.
Yeah. Okay. Yeah, you're close. If you're sending advertisements, if you're spamming 10 million people telling them, listen, if you buy this medicine, it'll make you prettier or something, or more, right? You want to send it to 10 million people. Using the datagram switching technique, you don't have to request each individual, say, hey, I'm going to send you an ad, and they have to confirm it to you. If you do it using this method, you'll probably be refused by almost everybody. With this datagram switching technique, you just send it to 10 million people. Some of them may not be there. Some of them may not even have their computer switched on. It will be lost. Some of them may be the wrong address altogether. There's no such thing as this address. But what? Out of the 10 million, 8 million people will get it. So in the case of advertising, maybe it's a better idea to use the datagram switching technique. Like if you work in a company now, an advertising company, and they say to you, listen, we're going to run some 10 million or 100 million advertisement. We have two networks ahead of us. Which one shall we use? Virtual circuit or a datagram? Well, in this case, if for advertising, it's probably a good idea to use the datagram because you don't have to get the permission of each individual customer that you're going to send them that ad. You just send it to 10 million, and you probably, maybe 8 million will get it. 2 million will be lost. That's fine. It's something you can live with. if you want to watch a video, no, if you want to listen to music, stream down, which one would you go for? Which one would you recommend? Datagram or virtual circuit? Hold on, I have a volunteer here. Why? Any idea? Yeah, because it guarantees a quality of service. Remember, videos and music, you want a good service. Good service, that means fast enough. It does not interrupt every now and again. It might start good with the datagram, but there is no guarantee it will continue. It might even be better than the virtual circuit, but 10 minutes later or 5 minutes later, it may not. Things can change on the internet. And next machine, and so on. So this is the way it works. The device or the file is sent in its entirety. The file is not broken into smaller units. It goes from one machine to the next until finally it reaches the final destination. Obviously, this is an extremely slow operation because of the use of the storage devices. Go straight to the datagram switching technique. If this is the network and these are the users, a file to be transferred, it's broken into small units. We call them packets or datagrams. They're given sequence numbers, and they're forwarded to the nearest gateway or router. And from there, it could follow any different route. Each packet is independent of the rest of the packets. They can go in different directions. They could go the same direction, the same route. There's no requirement. But just notice that the links in the network are shared, and the routing is flexible, and that's something else. If we are downloading, all these files and going through the same route, same this way, let's say they're flowing in this direction, what happens if this link breaks? It can follow a different route in the datagram switching technique. Remember, with the virtual circuit, like you're booking, it's like booking with Ryanair, or if you book a route and if you can't make it or for some reason it doesn't go, it's going to be very difficult to change it. In fact, here, we don't change it. On virtual circuit, it has that little problem. If a link breaks along, let's say it's not datagram, it's virtual circuit, that you must follow this route. And if this route breaks, then your call is terminated. You must start a new call. Okay, so that's a major difference between them. This is more flexible with routing. This can deal better with link failures. It will, just each router will know that this link is no longer available to direct the rest of your data through any other route. So once it breaks the data into packets, they'll go from one machine to the next, and they'll probably follow the same route, or they might go in a different route until they get to the final destination. They're assembled, the header is thrown away, and the file is created and delivered to the final user. Okay, this is a simulation for the circuit switching technique, the old telephone systems. If, for example, these lines, these phones that are connected to this on this road, that are connected to this switching box, if one of them wants to dial that phone there, they need to know the number for that phone. And to send data, you pass through three phases, and that's, first one is the call setup. So we need to do a call setup here. Call setup, you start picking up the phone and dialing the numbers that, to that phone number. Maybe I'll speed it up a bit. So once the number is dialed, it reaches the first switch. So the switch starts rotating, try to connect you based on the numbers you've dialed. So in this case here, the switch starts rotating, and it knows your number is connecting you to this switching box on another area in town. And then the signal goes to that box, switching box starts rotating and connecting you to another switching box, and can continue for a number of boxes until eventually it gets to the box that's connected to the phone that you need. And once the connection is made, then that phone starts ringing. And only if that phone is picked up, that now we say the call setup is done. Now we can start sending data. or talk or whatever it is. So in this case. And it will continue like that. Remember, this link now that's formed between this phone and that phone is one complete circuit, and it's dedicated only for those two users. Remember, the dedicated is only used on circuit switching. If you are asked to describe virtual circuits and you use the word dedicated, then you're going to be not in trouble, but your answer would not be 100% right. In datagrams, there's no dedication. In virtual circuit, there's no dedication. The dedicated line is only in phone circuit switching technique. So be careful with key words, like the word dedicated or shared. These lines are dedicated for the duration of the call. And once the call is terminated, then that dedication is gone, the switches go back to normal, ready to accommodate another phone call. And remember, if a line breaks down during the call, then that entire call is also lost. This is the point-to-point connection and connectivity, and that's probably the fastest way to communicate with anybody, is to talk directly. If you have a link between you, it's a dedicated link between those two. But if this guy wants to communicate with this machine as well, they must have another link, and that's a dedicated link. But of course, you can't connect with everybody in the city or in the country or in the world using this way. It's impossible to do. And also, if you have a connection with everybody, that link is probably idle, not used. Utilization is really poor because you're not always communicating with, say, with this device 24 hours continuously. So this is good for only 2 or 3 machines to connect directly with, but any more than that, it becomes inefficient. And then we go for a local area network where we can connect a group of machines and we can share the medium between them, whether it's a wireless transmitter or a cable between them. This is known as the bus topology. This is one way of connecting computers. You can have a switch with all these computers connected to it, and you can communicate, and it works well. But it has a limit as well. Maybe 50 machines, 100, 200 machines. Any more than that, it becomes really slow. So if this guy wants to communicate with this guy, those two have to wait. So if there are 300 machines on it, then you might end up doing a lot of waiting. So this is good to up to a certain range. And that's where then came up to switching. Where switching, it's a technique of allowing us more people to communicate with less resources.
Like a bus connector.
This one, they call this cable, they call it the bus, a bus kind of topology. Or that's one cable going around all the machines, and we use it to transmit the signal to any of the machines. You can transmit to any of the machine or to all machines. But in reality, this is what the world looks like. Lots of small local area networks around the world, and they're all interconnected with those devices. So if your machine, if you are a user on this local network, want to communicate with another user on this network, it will probably go through this router, maybe to this network, through this router, to that machine. So you must go through these devices. These are the devices that will do the switching, change in the direction of messages. This is probably a very nice and simplistic view of all the networks that are around the world. Still the datagram switching technique. Pass through that to the circuit switching technique. That's what the old telephone systems, the old switches look like. Mechanical switches. There are loads of switches here that rotate around to connect you to as many boxes and other switching boxes in the city. But the basic idea is something like this. You want to communicate with someone else, you go to the switch, and the switch, say, connects A to this switch here, and this switch will rotate around based on the address of D. Now you have a circuit from A to D, a dedicated circuit. That's the problem with this. It's the dedication. Is the route flexible here? This is the old telephone system. It is not. If a link breaks along that circuit between, or that phone call between A and D, the call is terminated. Even if it's reconnected, you must start a new call. You don't continue the same call. Then virtual circuits. In virtual circuit technique, we got rid of the dedication. All these links are shared. It gives a good quality of service. It guarantees the quality of service. Flexibility is not great, or dealing with broken links. If you are allocated a route and that route breaks, then the new implementation, yeah, you can have a standby route, but we're talking about the basic idea. You're allocated one route. Robustness, a robust system is a system which will continue to operate well despite if there are breakdowns or problems. This is not very robust. The datagram is more robust. The datagram, if you're sending data through one route and it breaks, we can change routes. So in the case of virtual circuit, first we send a request, and that will define the route you'll follow. But it's not dedicated route. It's just like booking your flight. You know where you're going. Everybody knows about you, but it's not dedicated for you. And you'll have to wait until a response is received. If your request is accepted, then we take your file, break it into small packets, give them sequence numbers, but also give them the virtual circuit number. And they all must follow the same route. If this link breaks, all communication stops for this particular call. And this is just given the example that I mentioned. If you're traveling, say, from Dublin to Turkey, there are many routes you can follow. And usually what defines the route, even same as in computer communications, it could be the cost, it could be the speed, it could be the frequency, it could be the error or failure rate, or say like if you're traveling and you travel through some route, and that route maybe they always suitcases are lost, so you say, all right, I won't go that way. Or maybe some route is cheaper to go, or more frequent, or more secure. These are considerations are also taken into the computer communication to pick up a route based on some factor.